Welcome back. Let's implement depth-first search using in-order, pre-order, and post-order. And we're going to start off with in-order first. Now, let's name this, let's call it depth-first traversal, or search in this case, and we'll say in order. Now, within here, we're going to use a recursion because, well, most of the time depth-first search is implemented using recursion because it's quite simple to do so, as you'll see. But if you remember from implementing breadth-first search, with recursion, because we're going to be calling this function over and over, we can't just declare variables inside of it because they'll be reset. So we're going to do the same thing as we did here. But to keep things clean and to also show you how different ordered depth-first searches work, because we're going to have 3 of them. We're going to have in order, post order, and pre-order. I'm going to create 3 separate functions down here describing these. So all I'm going to say in here is we're going to have return traverse in order function. This will be our recursive function. And DFS in order method simply returns whatever gives us this result. So in our case, we're going to add this.root, start off with our root node, and we're going to give it a list where our answers will be entered. And we're going to do the same thing for post order and pre-order, just naming them their appropriate ways. So let's write the first function. Traverse, if I can spell, traverse, post order, and pre-order. There you go. Let's start off with the first one. It's going to be a function called traverse in order that we created up above. That's going to get a node and some sort of data, or we can call it list in this case. Now remember that in order is going to give us the list of nodes in order, in sorted order. If we look at our tree, we want to ideally have 1, 4, 6, 9, 15, 20, 170. And the way we go about doing that is, well, first of all, we're going to check, hey, does the node have a left child? If it does, well then, we're going to traverse all the way down using recursion to node.left and pass data. Again, I know recursion can be tough to grasp at first, but all we're saying here is that if the node, especially the root node when we first start off, if it has a left child, which 9 does, then traverse all the way down. Keep going left, it's going to call this function, and it's going to keep going left until the node has no more children and we end up at 1. When we end up at 1, I want you to, well, list.push our answer, node.value. So once there's no more node left, that is, we're at 1, then go to the next step, which is to push this value 1 to the list. After that, we're going to do the same thing we did up here to the right. That is, we want to go to check the right now and say, hey, go all the way to the right until there's no more children. And now we have 6. And we go through this function once again. When we have 6, there's no left child, and it's going to push the current node value, which is 6, to the right. So let's actually console log this. And by the way, we want to return, remember, we want to return the list at the end. So I'm going to console.log node.value. And if I click run here, or let's make sure this works, so I'm going to say traverse in order. I'm going to comment out these 2 and say tree.dfs in order, and we're just going to run this. If I run this, I get data is not defined because, well, this has to be list over here. Pass the list. There you go. Let's run. And look at that. We have 1, 4, 6, 9, 15, 20, 170. And we see here the path that we took because I console logged here, right? We have 9, 4, 1, then 6, then we go back to 20, 15, then 170. But because we're pushing our answers to the list, after we've verified the left nodes and traversed all the way down, the lowest numbers get put into the list. Now, the beauty of this is that implementing the other two now becomes extremely easy because they're very similar. Just the order changes. So the next one, which is traverse, let's say, pre-order, the only difference now is that, well, we got to make sure that we recursively call the right name. The only difference is that with pre-order, we want to push at the very beginning before we get to the very left node. Because remember, in a pre-order traversal, we go 9, 4, 1, 6, then 20, 15, 170. We start with the parent first, and that's the order. So we push the parent first, which is 9, then we grab 4, then 1, then we get 6, then 20, then 15, then 170. Let's see if that works. I'm going to change this to pre-order. Make sure I spell that right. Pre-order, perfect. And then I hit run. And look at that. We went 9, 4, 1, 6, 20, 15, 170. In that order, in the list. Now here, you can pause the video and see if you can implement the last one yourself. It should be fairly simple, right? All right, I'm going to get going. The post order is going to be very similar. We'll say traverse, post order, we'll have the list push at the very end. And why is that? Because we check 1, 6, the left and the right, and then the top, 4, then 15, 170, 20, then 9. So the order, as the name suggests, is post, is at the end. So if I change this to post order now, and I hit run, we have, well, the wrong order because I need to make sure I change the names so it's recursive. So we say traverse, post order, not pre-order. And if I hit run, that's much better. We go 9, 4, 1, and we start adding this to the list. I go 1, 6, 4, then 15, 170, 20, and then 9. And if we print all of these out, and I click run, well, let's remove the console logs from here and just console log each one of these. If I hit run, there's our logs. We have the post order, we have the pre-order, and then we have the in order. All of them are depth first searches, just done in different orders. Now, I'll leave the code for you to explore here. Because it is recursion, it might take a bit of time to get your mind wrapped around it. But you see here that it wasn't that difficult. We implemented breadth first search, both iteratively and recursively, and we also used depth first search in order, post order, and pre-order. And if you think about it, it starts to become more and more clear, especially when it comes to depth first search. All we're doing is we're checking the left element and the right element, or the right node. So that is the left reference and right reference of each node. And sure, we're doing these actions in different orders sometimes, depending on which ordering strategy we choose. But we're still doing the same 3 things. We're checking the left, checking the right, or we're just pushing a node to our list, to our answer. And for those of you that may have realized, we're using a stack data structure right here with the recursion. Each of these functions are added to our call stack and will start to return as they reach the end. That is, there's no more left and right children. And this is important to understand because it shows the space complexity of depth first search. The amount of space that we need in terms of memory, unlike breadth first search, which used the queue, the height of the tree will tell us how much memory we'll need because the height of the tree will match the deepest recursive function. And that's what's going to be added to the stack as memory. So our memory consumption is O of height of the tree, which will give us the worst case scenario when using depth first search. So now that you understand better how these searches or traversal work, I encourage you to go step by step, code your own, see if you can add this to your tree data structure as well. Because the beauty is, once you know how this works, you also just learn how to traverse through a graph. Congratulations, and I'll see you in the next video.